All right, everybody, let's start. So welcome to 2024 Anatoly Larkin Award ceremony. So there are two awards for the junior researcher and the senior one. So today we have celebrated junior researcher. Before I name the winner, let me remind you who Anatoly Larkin was. I'm sure people of my generation do not need any reminders, but for the benefit of the students in the audience. So here is Anatoly, or Toля, as we know him. How do I do it? Right. You would think so. Yeah.
Nope. This.
This one.
What happened here?
Maybe. Okay. Yeah.
There. If we just click.
Okay. All right. So Anatoly was born in 1932, and he started his scientific career as a young student at the Soviet H-bomb project, where he worked under direct supervision of Andrei Sakharov, who later became known as Nobel Peace Laureate, and he is a father of Soviet H-bomb at the same time. So Sakharov quite soon realized that he has a quite exceptional student here, and he personally approached higher echelons of KGB to let this young guy leave H project, and he was transferred to Moscow to the Institute of Nuclear Physics, where he worked under supervision. His PhD and his postdoc was done under supervision of Arkady Migdal, also quite well-known figure in theoretical physics. Then he was transferred to Landau Institute for Theoretical Physics, where he worked for 30 years, and he was a director of a big division in this institute. And the last 10 years of his career was spent here in Minneapolis in W.I. Fine Theoretical Physics Institute. But that's why we here celebrate his career and award prize named after him. So scientifically, he had at least two very close encounters with a Nobel Prize, which didn't came through. So the first one came in '61 when he was a PhD student, when he wrote with Valentin Vaks, they wrote a paper on application of superconductivity to the problem of mass of elementary particles. Right. So by the way, notice it was published in July '61 and submitted in July 1960. And in the end of this paper, what they wrote is that after our work was sent to print, we became aware of the work of Yoshiro Nambu, which analogous results was obtained. So March 1960. So Yoshiro Nambu got a Nobel Prize for this very work, and Larkin didn't. Too bad. So another one was a work which has an unassuming title, Phase Transition in Uniaxial Ferroelectrics. And you can read the abstract. Similar results have been obtained in 4-dimensional, so they realized the importance of the 4-dimension. If you look inside the paper, you will realize that what they did is what we today know as a renormalization group. So all the formulas are already here. They just didn't do epsilon expansion as Ken Wilson did in the same year, actually. And again, Ken Wilson was awarded Nobel Prize for this work, and Toля Larkin did not. But nevertheless, so he went on to produce a flurry of marvelous results. I list just very few of them. condensation with non-zero momentum, which is known as FFLO mechanism. So L here stays for Larkin. Theory of fluctuating superconductivity, melting of a vortex lattice in superconductors by disorder, one-dimensional Fermi liquids, pinning of charge density waves with Patrick Lee, who was the first recipient of Larkin Award, by the way, theory of weak localization and anti-localization, and many, many other notable results. He was fortunate to have, or he was genius enough to produce a string of brilliant students. Younger people in the audience may know Roma Lyuchin, who is in Q Station, Viktor Galetsky, who is in University of Maryland, Chushun Tian is in Beijing, Igor Alener and Lev Yofi both in the Google quantum computing AI station. All right, that's who Anatoly Larkin was and why we celebrate his name. And this year winner is, the Oscar goes to Rahul Nandkishore from University of Colorado. So when I say Oscar, I literally mean it. Here's the Oscar. So Rahul received his PhD in 2012 from MIT, and he moved for a postdoc at Princeton, where he spent 3 years. And after that, he was hired by University of Colorado, and he's there ever since. So Rahul is known for many pioneering works in condensed matter physics. Probably most well-known are his works in many-body localization, ergodicity theory, which will be subject to some extent, I understand, will be subject of today's talk. That thinking led him to theory of glasses, and in particular, theory of what we know as fractons. Though that's a very peculiar many-body order, which was discovered in many quantum materials. Tensor field theories and many other things. He left his mark in these areas. And yes, I'm looking forward to hear his talk. Congratulations, and it's all yours.
Thank you, Alex. It's a great honor to receive this wonderful award associated with the great Anatoly Larkin. Also, great to be here and to have a chance to tell you about a program of research that I've been pursuing for about the past 10 years, a little more than 10 years at this point. Yeah. So, along the way, many people have been involved who I should thank. 5 I will single out for special mention. So this is my collaborator, Vedika Kemani at Stanford. This is my colleague, Andy Lucas at Boulder. My former postdoc, David Stephen, now at Continuum. My current postdoc, Oliver Hart. And my former student, Charles Stahl, now at Stanford. And also like many other people who are listed below who did not have room for their pictures on this slide. Okay, so what is the talk about? Well, and at the end of the day, I'm a condensed matter theorist, and the governing slogan of condensed matter is you take many interacting degrees of freedom, put them together, and you can get new sorts of phenomena which have no obvious analog in the behavior of sort of single particle systems. Yeah? And historically, the search for these emergent phenomena has focused on systems in thermal equilibrium, where by and large, the possibilities are well understood. It's not to say we understand everything in equilibrium, far from it, but at least we have a sort of general sense of what's possible and what's not. Yeah? In contrast, if we look at systems that are far from equilibrium, then like we're into here, there be dragons territory. where you can have really new sorts of stuff with no analog in thermal equilibrium. And I would say that understanding non-equilibrium phenomena, and especially understanding non-equilibrium quantum phenomena, is one of the great open challenges for condensed matter theory in the 21st century. Yeah? And in the course of this talk, I will try and convince you that making progress towards meeting this great challenge requires revisiting everything we thought we knew about statistical physics. So the way I'll structure the talk is as follows. I'll begin with a brief overview of the notions of quantum thermalization and ergodicity. Then I'll talk about ways of breaking ergodicity, and this will be the sort of main substantive portion of my talk. I'll show you 3 routes to ergodicity breaking, ordered both chronologically in the order of when they were discovered, and also in increasing order of robustness, in a sense that should become clear as the talk progresses. And then finally, I will conclude. So let's start by setting the stage. When you open textbooks on quantum stat mech, the way they start is you have a quantum system of interest, and it is coupled to some reservoir. That is not the setting I want to consider. Instead, the setting that I want to consider is I have a well-isolated quantum system of many interacting degrees of freedom. It's a quantum system, so it's governed by some wave function psi, or more generally a density matrix. And that wave function, or more generally density matrix, time evolves according to the Schrödinger equation, written down here. Time evolution is generated by a Hamiltonian H. And now we want to know, where does the long-time dynamics bring this system? Yeah. So conceptually, you can take the sort of classic setting where you have a system that's coupled to a reservoir, and you can put your reservoir inside the box, and treat it as a quantum system in its own right, which has its own quantum state, which is part of the entire system that you're trying to describe. But also precisely this setting of well-isolated quantum systems is extremely relevant nowadays to a whole host of sort of synthetic systems, where you have essentially well-isolated many-particle quantum systems at our disposal. Yeah? So we want to understand what the time dynamics of the system does at long times. And our basic expectation might be that, look, you have some complicated system, you wait a long time, and at long time, statistical physics should apply. And statistical physics says that you wait a long time and systems go to equilibrium. Yeah? But there's one problem which you might sort of immediately raise, which is that, look, the process of going to equilibrium is associated with the loss of memory of the initial conditions. So suppose you have a cup of coffee, you pour in some cream, you wait a while, it goes to equilibrium, it turns into some uniform light brown color, you don't know where the cream was poured in. Yeah? The process, once you've gone to equilibrium, you're fully characterized by a handful of parameters like temperature and pressure. In contrast, quantum mechanical time evolution is formally unitary, meaning it preserves all information about the initial condition for all times. Yeah? So there's some tension here, and how do we resolve that tension? And the way to resolve it is simply to note that, look, the Hilbert space in which the quantum state lives in is enormous, and most of the operators on that Hilbert space are not actually accessible to us. Yeah? The actually accessible measurements are typically few body observables in a local and real space. And so the meaningful question is, do the actually accessible measurements see thermal equilibrium or not? And if the only way to extract information about the initial condition is to measure every degree of freedom in the system, measure global operators, that's not something that we're ever going to be able to do. So do accessible measurements see thermal equilibrium at long times? And this leads us to the notion of quantum thermalization. And now I'll remind you of the notions of macrostates and microstates. Yeah? So a macrostate is characterized by measurable properties like temperature and pressure, whereas a microstate contains detailed information about every particle and what it's doing. Yeah? And the only thing we can measure is which macrostate it's in. But there's lots of microstates that correspond to a particular macrostate. And there's this foundational idea in statistical physics dating back all the way to Boltzmann, which is the idea of ergodicity, which is to say that essentially over time the system explores all of the microstates consistent with conservation. Yeah? So if particle number is conserved and you have a certain number of particles, then over time you'll arrange them in all sorts of different ways, and you'll explore all the microstates that are consistent with particle number conservation, let's say. Yeah? And if you have ergodicity, then you have a notion of entropy, where the entropy is the number of microstates associated to that macrostate. You have second law of thermodynamics, and you have all of the wonderful sort of results of statistical physics. But suppose that the ergodic hypothesis were false. Yeah? Suppose the system was not able to cycle through all its microstates. Yeah? Well, then, it's the foundational axiom of statistical physics doesn't hold. And so you take your textbook, you throw it away, and you start over. Yeah? So the rest of this talk is essentially going to be about ways in which the ergodic hypothesis can be false. Okay, so how can ergodicity be broken? So the oldest, and I should say that actually this entire talk is going to be focusing on quantum systems. Yeah? So there are analogs of these questions that can be asked in classical statistical physics. I'm not going to be talking about them. All my work's been in quantum systems, so I'll be talking about ergodicity breaking in quantum dynamics. So the oldest answer to how ergodicity can be broken in quantum dynamics is you could have an integrable system. So an integrable system is a system with an extensive number of conservation laws. Yeah? So what happens when you have an extensive number of conservation laws is Hilbert space, the space of states in quantum mechanics, breaks up into an infinite number of different symmetry sectors. Yeah? And states in one symmetry sector cannot evolve into states in a different symmetry sector because they have different symmetry quantum numbers. And so you don't have ergodicity in any conventional sense. You don't thermalize to any kind of conventional Gibbs ensemble. Yeah? However, this structure is very fine-tuned because generically you might expect that if you add arbitrary perturbations, which can break these huge number of conservation laws, then you'll reconnect the Hilbert space. And generically, you'll reconnect the Hilbert space on a time scale that will be just set by something like Fermi's golden rule. Yeah? So it'll be some low-order polynomial in the perturbation stream. Yeah? More recently, there's been discussion of quantum scars. Again, in a similar setup, something which can happen at special points in the space of Hamiltonians. You add generic perturbations, you'll typically restore ergodicity on some time scale which is low-order polynomial in perturbation stream. But then you could wonder if you can get robust ergodicity breaking. And by robust, I mean that at a minimum, there should be a time scale which is longer than any polynomial function of perturbation strength. And this talk is going to be about ways of getting robust ergodicity breaking, arranged both sort of chronologically in order of when they were discovered and in sort of increasing order of robustness. Yeah, so I would say that most of what I'm going to be talking about today is pertinent for synthetic systems. Yeah. So in fact, I'll even mention some experiments as I go along. But yeah, the experiments that I'll be mentioning are in cold atom systems or Rydberg systems or what you might call synthetic quantum matter. Okay. So let's start with the oldest of these, many-body localization. So this is a story that plays out in systems with strong quenched disorder. So quenched disorder meaning material inhomogeneity. What can happen is that excitations get trapped on disorder. They're sitting on the bottoms of deep minima or on the tops of little potential wells. They cannot move because moving would change the energy, and quantum mechanical evolution has to be energy conserving. So for single particle systems, this is what Anderson won his Nobel Prize for, and I came up with this idea all the way back in 1958. I don't know. There's certainly some long literature on localization in interacting systems, and of course, Boris is one of the great figures, in this history. But one thing that we've really come to sort of seriously appreciate in the past 20 or so years is that this is something that can happen even for interacting many particle systems at non-zero energy density. Yeah, in fact, even at energy densities that would correspond to infinite temperature if the system were to thermalize. Now, how robust is it? Well, first of all, you need perfect isolation, you need quenched disorder, you need energy conservation. Well, okay, maybe flow k, where energy is only conserved modulo flow k reciprocal frequencies is okay, but to zeroth order, you need energy conservation. And if you have isolation, quenched disorder, energy conservation, then it's robust to short-range perturbations in the following sense. There are exactly solvable points in the space of all Hamiltonians where the localization is exact. You perturb about those points, and generically you'll restore ergodicity, but the timescale on which you'll do so will diverge more rapidly than any polynomial function of the perturbation strength. Yeah? So typically it'll be an exponential function of perturbation strength. Yeah? So that means it's not analytic, so it's something that's sort of fundamentally non-perturbative. And for the special case of 1D spin chains, there's even an asserted proof due to Imbrie that the timescale may be truly infinite out to some finite perturbation strength. The proof is somewhat controversial. I don't want to go into it. And of course, the spin chain model will not be a good description out to infinite times anyway. But this is the sense in which many-body localization is robust. Why is it interesting? Well, I would say, there's many reasons why it's interesting, but one reason it's interesting is that it's the first model of robust ergodicity breaking in the sense that I just described. And it makes for a very interesting playground because if you just have localization in single particle systems, then single particle systems, the statistical mechanics is trivial. Whereas once you can have this in interacting systems, then you can have non-trivial statistical mechanics. Yeah? And to illustrate this, let's talk about spontaneous symmetry breaking. So the idea behind spontaneous symmetry breaking is that the state of a thermodynamically large system may not respect all the symmetries of a Hamiltonian. And the canonical setting for illustrating this is the transverse field Ising model. So the Hilbert space is spin 1/2 variables or qubits arranged in a line. The Hamiltonian takes the following form. Usually you don't have this last term, but if you don't have this last term, it's an integrable model. So I'm adding an extra term just to break integrability. The sigmas are Pauli operators acting on the spin 1/2 variables. And there's a global symmetry undertaking every z to minus z. Yeah? So that's the global spin flip symmetry, the global Ising symmetry of this Hamiltonian. And it's well known that the ground states take the following form: all spins up plus minus all spins down, plus some dressing by quantum fluctuations. And this spontaneously breaks symmetry. Yeah, so how do we tell that it spontaneously breaks symmetry? A couple of standard diagnostics. One is you pick one of these exact eigenstates, like the eigenstate with the plus sign. You take an operator which is charged under the symmetry, like sigma z, and you measure equal time correlation functions of this charged operator in these exact eigenstates, and you ask if those correlation functions have long-range order in space. Another possibility is you can prepare an initial condition which explicitly breaks the symmetry, like you prepare the superposition state with all spins up. Yeah? And then you look at charged operators on one side, and you look at their autocorrelation functions in the time domain. Yeah? So sigma z on one side at time 0, sigma z on the same side at time t, and you ask if these autocorrelation functions have long-range order in the time domain, or if the dynamics of the system sort of restores the symmetry. And with both of these standard diagnostics, the ground states of the transverse field Ising model spontaneously break symmetry. Yeah? But it is also known that the excited states do not spontaneously break symmetry. Yeah? And in fact, there's theorems in StatMech, in this case, it's the Landau-Peierls theorem, which says that you cannot spontaneously break a symmetry in one dimension at any non-zero temperature. Yeah? And the argument is very simple. So if you move away from the ground state, you'll have places where the spin pattern changes from up to down. At the boundary of those, there's a domain wall. The domain wall can be placed anywhere in the system, so it has an entropy that's logarithmic in system size. The energy cost is constant. Yeah? So at any non-zero temperature, entropy beats energy. And so you make a ton of these domain walls, they run around, and they allow the correlation functions to relax. Yeah? This is something that Landau and Peierls realized almost 100 years ago, and sort of proved a theorem saying that at any non-zero temperature in one dimension, you cannot spontaneously break a symmetry. Yeah? Okay, fast forward to the 21st century, we'll consider the exact same Hamiltonian, but now we'll take the coefficients to be random, drawn from a distribution of sufficiently large width. And now what can happen is that with these coefficients random, and with enough randomness, you go into a many-body localized regime. And in the many-body localized regime, the excited states also take the form of some particular spin pattern, plus or minus its all spins flipped counterpart, plus some dressing by quantum fluctuations. And with these sorts of excited states, you go and you look at these standard correlation functions, equal time correlation functions in the exact eigenstates, or you prepare a particular spin pattern, and then you look at autocorrelation functions. These correlation functions have long-range order, yeah? Which suggests that symmetry is being spontaneously broken. Yeah? And isn't this something that was supposed to be forbidden by the Landau-Parels theorem? Well, yeah, but the Landau-Parels theorem assumed ergodicity, which we don't have in the many-body localized regime. Yeah? So specifically what's going on is in the excited states, you have these domain walls, but the domain walls cannot run around because they're localized on disorder. Yeah? So as a result, there's no entropy. Yeah? And because the domain walls cannot run around, they cannot allow the correlation functions to relax. So you can spontaneously break symmetry outside the ground space. In fact, you can even spontaneously break the symmetry in very highly excited states, and even states that would correspond to infinite temperature if they're thermalized, which they do not. Yeah? And this is something that was nominally forbidden by Landau-Parels, but Landau-Parels made assumptions which are not applicable in this setting. So now the Ising model example I gave you is sort of historically the first example of spontaneous symmetry breaking of a type, or of ordering of a type that could not happen in thermal equilibrium, but can happen in the ergodicity breaking regime. There are others. The most famous certainly is time crystals. Not going to talk about time crystals, but suffice to say that there are new things that can happen once you break ergodicity. Yeah? Now you could wonder, is many-body localization the only game in town, the only way to robustly break ergodicity? Well, 10 years ago, it was the only one we know of. Since then, we've discovered others. So now let's talk about alternative routes to ergodicity breaking. So the first of these is ergodicity breaking from what I'll call fractonic symmetries. So this is something that was inspired by the study of fracton phases of matter. Now, fracton phases are sort of exotic quantum phases of matter. You could think of them as generalized spin liquids, but for the purposes of this talk, you don't need to know anything about fractons. Yeah? Just they were the sort of, as it so happens, they were the inspiration for us to discover this. But the bottom line is that this is a completely different route to ergodicity breaking. Yeah? Nothing to do with localization. It does not require energy conservation. It does not rely on disorder. Instead, it comes about as a result of the interplay of finitely many conservation laws. I say finitely many, but in fact, 2 are sufficient if you pick the right 2. And the right 2 to consider, for instance, are, say, conservation of charge and dipole moment. Yeah? So everything, and we also need strict locality. Okay, so it's nice to illustrate things by example. Everything should be illustrated first in the simplest possible setting. And the simplest possible setting here is we consider dynamics in one space dimension. Yeah? So we have a one-dimensional chain. It's convenient to make it spin 1. Yeah? So we're going to consider one-dimensional dynamics, which is locally generated and which conserves 2 quantities. So it conserves the charge, yeah, and it conserves the dipole moment of the charge. So if this is a spin chain implementation, then say the z component of the spin could be a conserved charge. So we could demand that the dynamics conserves the total charge, and it also conserves the dipole moment, which is just the position-weighted charge. Yeah? It's charge and dipole defined in the usual way. So what does this imply? Well, first of all, if you have a single charge is immobile, because if a single charge hops either right or left, that would change the dipole moment of the state. And dipole moment is a conserved quantity by, because we've declared it to be. However, if you have a plus and a minus charge next to each other, that can move freely. Yeah? So a bound dipole is a mobile object. And you can also have this sort of process, which you could interpret either as charge hops left and emits minus plus dipole to the right, or charge hops right and emits plus minus dipole to the left. So we want to consider dynamics, which has these 2 conservation laws and is locally generated, but we want to impose no additional structure besides that. Yeah? So the simplest way to do that is to use what's called circuit model dynamics. So you have a state, and the dynamics is generated by acting with some local unitary operators. In the quantum information world, these would be called gates. But if you're not used to thinking about circuit dynamics, you could just think of the Suzuki-Trotter decomposition of the time evolution operator, and take each of these layers as one layer of the Suzuki-Trotter decomposition. Yeah? So you have these local unitary operators which generate the dynamics, and they're constrained to conserve the charge and the dipole moment. But other than that, I impose no structure. So I could choose them uniformly in space or randomly in space. It won't affect the answers. I could choose them uniformly in time or randomly in time. It won't affect the answers. Maybe for maximum drama, what I should do is I should choose them uniformly in space, so there's no disorder, and randomly in time, so there's no energy conservation. Yeah? Because remember, in Noether's theorem, energy conservation is tied to time translation invariance. I don't have time translation invariance. I don't have energy conservation. What should you expect? Well, this is minimally structured dynamics. What you might expect is ergodicity. So if you look at the charge distribution in the system, you look at the long time average. The long time average should look like equipartition over all states in a given symmetry sector. Yeah? And if you look at the equipartition distribution, it looks like these two plots over on the left. Basically, the charge distribution should be flat over the whole system. Yeah? But now you set the system up with charge at a particular site. And you see what happens. And what you observe is that, in fact, the charge does not spread very far. It spreads a little bit, but it stays kind of close to where it started. Yeah? So in fact, it appears empirically, numerically, that we have something that looks like localization of charge. Yeah? And for this minimal implementation that I showed you, in fact, charges are localized for almost any initial condition. Whereas for longer range gates, if you allow sort of bigger operators to generate your dynamics, typical initial conditions might seem to thermalize, but there is still a subspace exponentially large in system volume, which does not. And I will emphasize that this cannot be conventional localization, either Anderson or MBL, because there's no disorder and there's no energy conservation. Yeah? So the underlying mechanism has to be something completely different. So what is it? Well, we sort of figured it out about a year later. I will share it with you. So actually what's going on is very simple and is coming about from the interplay of these conservations. So we have a system with a bounded Hilbert space. So there's a locally maximum positive charge, call that plus, a locally maximal negative charge, call that minus. And now let's consider a state which alternates between all plus and all minus regions, with the domain walls separating plus and minus regions at least as far apart as the biggest operator that generates my dynamics. Yeah? So if the biggest operator that generates my dynamics has spatial scale m, then the domain walls are at least m apart. So now I come in and I generate my dynamics. My operators act across either 0 or 1 domain walls, never across 2 because the domain walls are too far apart by construction. If you act across 0 domain walls, then you act on a region that's locally extremal charge. Nothing you can do to that consistent with charge conservation. If you act across 1 domain wall, you act on a region which is locally extremal dipole moment. Nothing you can do to that either, because if you try and shuffle the charges around, it would change the dipole moment. Yeah? So any state of this sort must be an exact eigenstate of any dynamics with these 2 conservation laws plus spatial locality. Yeah? How many states like this are there? It's easy to place a lower bound. You carve your system up into blocks of size m, allow each block to be either all plus or all minus, and you're guaranteed to have a state which is a simple product state and is also an exact eigenstate of any dynamics with these 2 conservation laws and locality. So you have a number of states which is exponentially large in system size. Yeah? This bound is not tight. There's a coefficient here, which you can get from doing transfer matrix, but it doesn't matter. It's exponential. Yeah? The number of symmetry sectors is only polynomial. So there's polynomially many symmetry sectors, but there's exponentially many states which have no dynamics. So they cannot be living in different symmetry sectors, right? There's sort of additional structure here beyond just symmetry sectors. So ergodicity is being broken. All of this generalizes to higher dimensions. Essentially, if you're in d dimensions and you conserve both charge and all d components of dipole moment, then you have a number of states which is exponential in system volume, such that if you start in this exponential in system volume subspace, there's no subsequent dynamics. So let's get a little bit more quantitative. In quantum mechanics, time evolution is generated by a unitary matrix. And this unitary matrix is block diagonal by symmetry sector. Yeah? So a state with one set of symmetry quantum numbers cannot turn into a state with different symmetry quantum numbers. Yeah? So states with different symmetry quantum numbers live in different sort of symmetry blocks. But if it's an ergodic system, that's it. Each symmetry block should just be a random matrix. Here we have a whole lot more structure. So the unitary matrix is still block diagonal by symmetry sector. But on top of that, within each symmetry sector, it further block diagonalizes into exponentially many Krylov subsectors, yeah, such that a state in one Krylov subsector never evolves into a state in a different Krylov subsector, even if both states have the same symmetry quantum numbers. Yeah? So this is the sense in which ergodicity is being broken. Within each symmetry sector, Hilbert space is breaking up into exponentially many subblocks, such that whichever subblock you started in, that's the subblock you always stay in. You're not able to explore other states with the same symmetry quantum numbers unless they're in the same subsector. There's a very broad distribution of block sizes, so there's special states I was showing you before are sort of 1-by-1 blocks. They don't mix with anything else. There's other blocks with size 2, 10, 500, 30, 5 million, some with size that diverges in the thermodynamic limit. Yeah? So this phenomenon is called Hilbert space shattering or Hilbert space fragmentation. And Hilbert space is breaking up into subblocks which have the same symmetry quantum numbers, but states in one cannot evolve into states in a different one. Yeah? And this structure is robust to any perturbations that respect these two symmetries and strict locality. Now, you might think that charge and dipole are very weird symmetries. Like, how would you possibly get this? In fact, there's a very natural realization. The natural experimental realization is you take cold atoms in an optical lattice, and you tilt the lattice. Yeah? The number of atoms is conserved. That's just particle number conservation or mass conservation. Yeah? That's the analog of charge conservation for me. And because the lattice is tilted, the center of mass is also conserved. Because if the center of mass moves uphill or downhill, that changes the energy of the system if the tilt is really strong. Yeah? And the energy is being conserved here because at the end of the day, we're doing Hamiltonian dynamics. So if energy is conserved and the tilt is strong, then the center of mass cannot move. Yeah? So you get number conservation, but you also get center of mass conservation. And center of mass is analogous to dipole. Yeah? So mass conservation and center of mass conservation is exactly analogous to charge conservation and dipole conservation. And in this way, you can actually realize the physics I was talking about with cold atoms and optical lattices, where you tilt the optical lattice. Yeah? And in fact, this has already been observed by multiple groups. Yeah? And there's sort of other proposed realizations. There are no phonons, correct? Yeah, optical lattice. Yeah. So what have we accomplished? Well, we found an alternative route to ergodicity breaking through this mechanism of so-called Hilbert space fragmentation. It does not rely on energy conservation or on disorder. Instead, it relies on the interplay of two symmetries and strict locality. Yeah? Now, brief aside, I said that the time evolution matrix block diagonalizes into dynamically disconnected subsectors within each symmetry sector. Some of those subsectors are small. Those are the ones I was talking about before, the states which don't time evolve. But I also said that there were some large subsectors, some subsectors with size that diverges in the thermodynamic limit. And for those large subsectors, the dynamics is actually thermal with respect to the subsector. Yeah? It's not thermal in the usual sense where you explore the entire symmetry sector, but you explore the entire subsector, and the subsector itself is infinitely big. So you can define a sort of modified notion of thermalization with respect to the subsector. And now you can ask about how you approach thermal equilibrium. Yeah? So the standard law says that if you have a system with conserved charges, then the approach to thermal equilibrium should be governed by hydrodynamics. Yeah? And the canonical behavior sort of at long times will be diffusion. So what I've written down here is the diffusion equation for a conserved charge density rho. And this diffusion equation, you can just do dimensional analysis. It has this characteristic relationship between length scales and time scales, where length scales go like square root of time. Yeah? So if you start with charge over here, it'll spread out, and it'll spread out as square root of time. Yeah? That's normal diffusion behavior. So in the present context, where you have, let's say, charge and dipole conservation, well, the approach to equilibrium is still given by hydrodynamics, but it's not normal hydrodynamics. It's not diffusion. Yeah. Instead, what you get is subdiffusion. Yeah. And in fact, it turns out there's like new hydrodynamic universality classes. In fact, infinitely many new hydrodynamic universality classes, which can be accessed in this way, all of which exhibit subdiffusion. So let me now illustrate how that comes about. Now, this structure is very robust. So there's actually a very easy way to see that it has to be subdiffusion. So the easy way to see it is that, remember, the mobile objects in this theory are dipoles, not charges. Yeah? And dipoles do not move in response to a uniform field. So if you apply a uniform electric field, dipoles feel no force. Yeah? So the conductivity of this system must be 0. If the conductivity is 0, then by the Einstein relation, the diffusion constant must be 0. So whatever's going on has got to be slower than diffusion. Yeah? What is going on? Let's try and figure it out. Okay, well, the first thing we need is the continuity equation. Yeah? So there's the conserved charge density, and the only way the charge density can change if there's some divergence of current. Yeah? But the current now is a 2-index object because you have dipole in direction I moving in direction j. So just to balance indices, you better have 2 derivatives. Yeah? In principle, you could derive this from the Ward identity of a Schwinger-Keldysh functional description, but just to the level of counting indices, like the indices have to match, so you need an extra derivative. The other thing we need when we're doing hydrodynamics, now besides the continuity equation, is you need a constitutive relation. So you need to know how the gradients and charge density turn into currents. So that too you can figure out. Essentially, dipoles move in response to gradients in the electric field. Yeah? Gradients in the electric field mean 2 derivatives of the scalar potential. So 2 derivatives of the charge density. So the constitutive relation also has an extra derivative in it. Yeah? And when you plug that back in, you get 1 extra derivative from the continuity equation, 1 extra derivative from the analog of Fick's law. And so instead of having diffusion equation with a Laplacian, you get a modified diffusion equation which has square of the Laplacian. Yeah? And more generally, if you conserve the first n multipole moments, then you get an equation of the following form. So here n is 0 as you conserve charge only. That's the ordinary diffusion equation with 1 power of the Laplacian. N is 1 as you conserve charge and dipole. That's 2 powers of the Laplacian. N is 2 would be you conserve charge, dipole, and quadrupole. 3 powers of the Laplacian, and so on. Yeah? So every time you add an extra multipole, you get an extra power of the Laplacian. Now you go to dimensional analysis, and you will conclude that length scale goes like time scale to this tunable power, which depends on n. So there's an infinite number of different universality classes, and all of them are subdiffusive, because as long as n is 1 or more, this is slower than square root t. Yeah? So there's an infinite number of subdiffusive hydrodynamic universality classes, which can be accessed by turning on conservation of additional multipole moments of charge. And this too can be realized with cold atoms in tilted optical lattices. And in fact, at least the the dipole conserving, like t to the 1/4 part of it, has been observed already by the Princeton ultra cold atoms group. Okay. That was an aside. Let's get back to the main story. So the main story is about ergodicity breaking. First, I told you about many-body localization, which was a route to ergodicity breaking, which requires energy conservation and strong quench disorder. Then I talked about this other phenomenon of Hilbert space shattering or Hilbert space fragmentation. Needs 2 conservation laws. Both of these are robust to geometrically local perturbations. Yeah? Now, you could wonder, can you get ergodicity breaking, which is robust to geometrically non-local perturbations, like arbitrary perturbations, without even demanding spatial locality? Yeah? So if you'd asked me 5 years ago, I would have said, this feels like an impossible ask, but now we know how to do it. Yeah? And the trick to getting this to work is what are called higher form symmetries. So we're used to thinking about global symmetries. Symmetry operator acts everywhere in space. We're used to thinking about gauge symmetries. Symmetry operators act on points. Higher form symmetries are intermediate between the two. the symmetry operators act on deformable subdimensional manifolds. Yeah? And the charges of these symmetries are extended objects. And when you have these higher form symmetries at play, then you get ergodicity breaking with topological stability and very simple geometric proofs. So let me illustrate now how that works. All we're going to require for this final part of the talk is enforcement of a single constraint. If the single constraint is enforced exactly, the results will be exact to infinite times. If the constraint is imposed softly, meaning you're allowed to violate it, you only have to pay some large energy penalty to violate it, then we'll be able to place pre-thermal bounds, so there will at least be an exponentially long time scale out to which the results will be valid. And at the end, I'll maybe even talk about how we could maybe get this time scale to be truly infinite. Okay, again, everything should be introduced first from the simplest possible example. The simplest example here is what we call the CZP model. So the Hilbert spaces, you have spin 1/2 variables on the vertices of a square lattice. The Hamiltonian is H0 plus V. V represents perturbations. And I assert that this Hamiltonian is going to break ergodicity for arbitrary V as long as V is K local. So what do I mean by that? Well, V could be sum of Pauli X on every site. It could be sum of X on sites I, Y on site J. I and J don't have to be close to each other. They could be sort of infinitely far apart. Yeah, it could be Xi, Yj, Zk, whatever. The only requirement is that this term can be expressed as a sum of terms where every term in the sum acts on only finitely many degrees of freedom, at most k degrees of freedom, where k is something bounded. Yeah? So I'm not allowed completely global perturbations. My perturbation should be expressible as a sum of terms where every term in the sum acts on finitely many degrees of freedom, but it does not have to respect any symmetries, and it does not have to be spatially local. Yeah? So it's a very minimally structured set of perturbations, and I assert that for any such set of perturbations, this Hamiltonian is going to break ergodicity. So obviously, much depends on what H0 is. Yeah? So what's H0? Well, H0 is this term, I mean, sum over all plaquettes, this operator we call CZP. If you're from a quantum information background, you can think of CZP as product of controlled Z-gates around the 4 links of a plaquette. If you're from a condensed matter background, it's made up of Pauli Z operators in the following way, where I, J, K, L are ordered going around a plaquette. Yeah? So let's say anti-clockwise around a plaquette. So it's some operator. And what it does essentially is it penalizes having an odd number of neighboring upspins around any elementary plaquette. Yeah? So you pick your elementary plaquette, and you should not have an odd number of neighboring upspins. So that's like essentially this term, if you make J large, what it's doing is it's enforcing a constraint that you do not have an odd number of neighboring upspins around any elementary plaquette. Now, how large is the constrained Hilbert space? Yeah, so the constraint satisfying subspace, one can show, has dimension which is exponentially large in system volume. Yeah? So if you take log of the constrained subspace dimension, that is an extensive quantity. That's important because it means a subspace is big enough to accommodate a non-zero entropy density. Yeah? So this constraint satisfying subspace is big enough that it's sensible to talk about thermalization or lack thereof within the constrained subspace. Now, to understand what's actually going on, it's convenient to introduce a dual representation. This basic Hamiltonian, which I introduced, has 2 Ising symmetries. So it's defined on the square lattice, which is bipartite. There's an odd and an even sublattice. You do global Ising spin flip on either the odd or the even sublattice, and nothing changes. Yeah? So we'll go to some set of domain wall variables where there's one set of domain walls for the Ising symmetry on the odd sublattice. We'll call those the red domain walls. There's another set of domain walls for the Ising symmetry on the even sublattice. We'll call that the blue domain walls. And the constraint, which I just stated, is equivalent to saying that the red and blue domain walls cannot intersect. Yeah? So in this dual representation, my constraint satisfying Hilbert space consists of 2 species of closed loops, red and blue. Yeah? They're closed loops because domain walls cannot terminate inside the system. Yeah? Domain walls have to be closed loops. So 2 species of closed loops with a non-intersection constraint which says that red and blue loops cannot intersect. But they can fluctuate any which way, subject to this constraint that red loops cannot intersect blue loops. Okay, now let's consider a state of the following form. So what this is meant to be is a dense packing of non-contractible loops, so loops which stretch all the way across the system, which alternates in color, red, blue, red, blue, red, blue. There's lots of densely packed configurations like this because essentially, this pattern can wiggle every which way. Roughly every row, these loops can march either right or left. So that gives you a number of patterns which is exponential in system size. But once you've made a densely packed configuration like this, any subsequent fluctuation or perturbation is going to create loop intersections, which is the thing you were not allowed to do. Yeah? And the only way to change this pattern and stay in the constrained subspace is either to put a kink in the entire pattern or to delete an entire non-contractible domain wall. But either of those things involves acting on order L degrees of freedom, where L is being taken to infinity. And you only have at your disposal things which act on finitely many degrees of freedom at a time. So you cannot do this at any finite order in perturbation theory. If the constraint is being imposed exactly, then that implies that these states are true eigenstates, they live forever. If the constraint is being imposed energetically, meaning you're allowed to violate it, you just have to pay some large energy penalty, then you can rely on you can sort of map this onto the rigorous theory of prethermalization to establish a bound, which is exponential in perturbation strength, and there's some exponentially long time scale out to which these states are metastable. Yeah? So we have this apparent ergodicity breaking to exponentially long time scales. Now, I've been asserting ergodicity breaking, but you could say, well, hang on, are you sure you have ergodicity breaking here? Because after all, you have to resolve by symmetries. And if you start this problem, there's actually a higher form symmetry here, so we should be resolving by higher form symmetries. So if you resolve by higher form symmetries, you take your time evolution matrix, it block diagonalizes into symmetry sectors, and you find there's two sorts of symmetry sector. So all of these blocks are labeled by quantum numbers of this higher form symmetry. Yeah? So there's one sort of symmetry sector in which the dynamics is ergodic, and in fact, it's basically governed by magnetohydrodynamics. So we've got a higher form symmetry. The symmetry charges are loop-like objects. The hydrodynamics of loops is magnetohydrodynamics. Yeah? But then there's another sort of symmetry sector, which is made of these densely packed configurations. And in this other sort of symmetry sector, there's no dynamics whatsoever. Yeah? So there is ergodicity breaking, but it's sort of all or nothing in character. There's some symmetry sectors which are ergodic. There's other symmetry sectors which have no dynamics whatsoever. This all or nothing nature is particular to this very simple model, and we can get away from it. So one way to get away from it is instead of having Ising spins, we can switch to clock spins. So you have M-state clock spins instead. Now, essentially, instead of having 2 colors of domain walls, you have M colors of domain walls. So M is 3 is sufficient. Let's say you have red, green, blue domain walls. Again, the constraint is that domain walls of different colors cannot intersect. The constraint satisfying Hilbert space is still exponentially large in system volume. The low energy constraint satisfying Hilbert space is still a Hilbert space of colored loops in M colors, subject to the constraint that loops of different colors cannot intersect. But now, let's imagine doing the following. Here's a state. It is a constraint satisfying state because loops of different colors never intersect. Yeah? Let me walk from left to right across the system. Every time I encounter a non-contractible domain wall, I will record the color. Yeah? So for this state, I would record green, red, or if I wish, GR. Yeah? Each non-contractible domain wall that I encounter is a letter, and that ordered string of letters is a word. Yeah? That word is a topological invariant. The only way that word can change is I would need to either push one domain wall through another, which would involve violating the constraint order L times, or I would need to insert or delete a non-contractible domain wall. Either of those things requires acting on order L degrees of freedom, and I only have stuff that acts on finitely many degrees of freedom at my disposal. Yeah? So this word is a topological invariant, and it cannot change under any k-local constraint satisfying dynamics. The number of symmetry sectors is polynomial in system size, but the number of possible words I can write down is exponential in system size. Yeah? So it's words in M letters, where the word has length at most L. So there's exponentially many possible words. So that indicates that ergodicity is broken And moreover, one can show that you can insert finite thickness motifs, which are symmetry neutral, but have a non-trivial word associated to them. Yeah? So now, in fact, every symmetry sector ergodicity is broken. So it's not all or nothing. You just pick a generic symmetry sector, and the unitary time evolution matrix within that symmetry sector, it block diagonalizes into exponentially many subsectors, where each subsector is labeled by a different topological invariant, and a state labeled by one topological invariant cannot turn into a state with a different topological invariant. Yeah, so ergodicity is broken, and this time it's broken with topological robustness, so we don't require spatial geometric locality anymore. Okay, so far I was showing you stuff on square lattice. You can generalize to arbitrary lattices by imposing a single constraint on elementary plaquettes. This also allows you to generalize from these loop soup type states I was talking about to a broader class of states which look like string nets and sponges. There's lattice-induced phenomena, which are very interesting, but I don't have time to talk about. You can generalize again to arbitrary graphs. So like that's a direction in which you can extend. Yeah? Now, all of this, if the constraint is imposed exactly, the results are exact. These are eigenstates. Ergodicity breaking persists to infinite times. What if the constraint is imposed energetically instead, meaning you're allowed to violate it, just paying some energy penalty? In that case, I said previously that you could place a bound that the time scale is at least exponentially long. Yeah? Can you do better than exponentially long? Can you get truly infinite time scales? So in fact, we think you can do that. And we think the way to do that is to use this recently discussed notion of what are called exact emergent higher form symmetries. So we have this model which in 2 dimensions we believe gives exact ergodicity breaking, meaning true to infinite times at 0 temperature. Yeah? So things like 0 temperature exact ergodicity breaking, these are known before. So 10 years ago, Isaac Kim and Jung-Won Ha wrote down a model which they proved has exact ergodicity breaking at 0 temperature in 3 dimensions. Now we can get it in 2 dimensions. Yeah, so that's a little bit of an advance. The bigger advance is now when we go up to 3D, we have this other model we call the rainbow membrane soup, which we believe gives exact ergodicity breaking even at non-zero temperature, and moreover, even when coupled to a non-zero temperature heat path. Yeah? And this is the first example that I know of where you get something which looks like ergodicity breaking to infinite times, even when coupled to a non-zero temperature heat path. Full disclosure, I think these results are correct. Certainly we have sort of what seem to me like solid physics arguments, but I do not claim to have proven this. So like rigorous mathematical proof here is still needed. Okay, so I think that brings me to my conclusions. Textbook statistical mechanics assumes you have ergodicity. If ergodicity is broken, then you are in terra incognita. This talk has been about ways of robustly breaking ergodicity in quantum dynamics. I've talked about 3 ways to do it. The first was many-body localization, means energy conservation, perfect isolation, quench disorder, robust to local perturbations. The second was fractonic symmetries, interplay of 2 symmetries, doesn't need quench disorder, doesn't need energy conservation, but it does need these 2 symmetries and still needs spatial locality. And finally, I've talked about this sort of higher form symmetry, root to ergodicity breaking, only requires a single constraint and can tolerate spatially non-local perturbations. Yeah. Now, maybe I'll stop there and just say that, look, this sort of general set of questions regarding ergodicity breaking and non-equilibrium quantum dynamics is very interesting. We continue discovering new things. So I think this is a sort of gold mine, which is by no means mined out. So look forward to seeing what comes up in the future. Glad to take questions.
Andrei, you couldn't be more far away.
Okay. Yeah. 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 Correct. Yeah.
About the way to interpolate from one level to the other and what happens in
Yeah. So how do you go from the many-body, I mean, you can from the many-body localized regime to the non-many-body localized regime. So this is the whole world of the so-called many-body localization transition. There is an enormous literature on this. I do not think the question is settled. Yeah, okay. So if Embry is correct, yeah, and many-body localization in spin chains is exact out to some non-zero perturbation strength, then there will be a finite regime of disorder. So at infinite disorder, everything is trivial, and you can back off infinite disorder, and there will be some critical disorder strength where this fails. But out to that critical disorder strength, as long as your disorder strength is supercritical, you'll have many-body localization, and you'll have spontaneous symmetry breaking in the exact eigenstates. Suppose that Embry is wrong. Yeah, I don't know what the mistake would be, but suppose there's some mistake in Embry's proof. Yeah? In that case, these would not be exact statements. And then at finite disorder, the timescale would not be infinite, but it would be merely exponentially long in disorder strength. And then this would be valid out to exponentially long timescales.
Sure.
Thanks. Right. So for the fractonic symmetries, does there have to be a very specific relationship between the two or more symmetries that you pick? Yeah.
Yeah, it needs to be the right two. So if just pick any two symmetries, generically it won't do it.
Right. And so does that tell you something more about what the what the limits are, what the constraints are?
So, I would say that so there's by now there is some fairly large literature on Hilbert space fragmentation. Most of the examples thereof are somewhat fine-tuned, and the most robust exemplars all involve multiple moments, what could be reinterpreted as multiple moments of some abelian U1 charge. Yeah, it has to be U1. It cannot be Z2, and it has to be abelian. Actually, the reason it has to be abelian is itself somewhat interesting. Actually, maybe I even okay. So suppose it was SU2. Yeah. So if it was SU2 and you had conserved you conserved the charges X, Y, Z, and also their dipole moments. Yeah. So now, if you look at the commutator of X dipole with Y chart or with Y dipole, yeah, that would be Z quadrupole, right? And similarly, the commutator of X dipole with Z dipole would be Y quadrupole. So you would get quadrupole conservation as a derived conservation law. But then you look at the commutators of the quadrupoles with the dipoles, and that would give you octupole conservation. And then you look at commutators of the octupoles with the dipoles, and then it would give you hexadecapole conservation. And so you would end up concluding that the moment you impose dipole conservation on, let's say, the SU2 problem, you would actually immediately impose conservation of every multipole moment, which means your dynamics is completely trivialized. Yeah. So that's why it has to be U1.
So let me ask you. In classical statistical mechanics, people are used to play with non-ergodic models for ages, like traffic jam models or cellular automata or pattern formation. Jorge here was involved in this business. So what's special about quantum mechanics?
Yeah,
what new do we learn about it?
To some extent, I would say that everything I talked about has analogs in just Markov chain dynamics, right? So you could write down models of Markov chain update rules on sort of finite state systems. And everything I talked about would have analogs in that setting. So it sort of has classical analogs. At the same time, it's a little bit harder to get ergodicity breaking in quantum mechanics because you could have tunneling, right, through classical barriers. So the fact that this still works in the quantum setting is a little bit more non-trivial, but it absolutely has classical analogs. Yeah.
More questions? Anybody? Fiona?
So I noticed when you introduced the Control Z plaquette model that you had a slide and you didn't talk about it, that was making a connection to Rydberg blockade.
Yes.
Is the claim that that is a model of Rydberg blockade?
It is not literally a model of Rydberg blockade, but it's closely related. So essentially, Rydberg blockade, no, you don't flip you don't allow your spin to flip if you have any upspins nearby. And here, you don't allow your spin to flip if you have an odd number of neighboring upspins nearby. So it's slightly different to Rydberg blockade, but yeah, it's very closely related. And like there is actually a known way to get this sort of constraint in Rydberg systems. So there's papers from Zoller with here's how you build this sort of constraint in. Yeah, so it's very much a Rydberg-inspired constraint.
Thanks.
If no more questions, then let's thank the speaker again and congratulate him. Thanks.